So there's remarkable symmetry in this pattern.
Hello, thank you. Thank you. Welcome. Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. And welcome to Perimeter Institute's public lecture series. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a sincere pleasure to welcome everyone here this evening. Both those of you here in the live studio audience, and also those of you watching online, either on Perimeter's website or on one of our many science and communication website partners around the globe. The lecture today will last approximately 1 hour and will be followed by a question and answer session. For those of you online, Dr. Kelly Foyle and her team of PI researchers are behind their keyboards watching the Twitter feed and our Facebook page and ready to engage and answer questions, engage in discussion throughout the lecture. If you want to participate, use hashtag #PILive. And for those of you who want to ask questions from online at the very end, I will also take questions for Neil via the Twitter feed. And now, it is my distinct pleasure to introduce tonight's very special guest speaker. We are honored to have Perimeter Institute's own Neil Turok launch this year's public lecture season. Neil has been a catalyzing force since joining Perimeter as director in 2008, and his lecture tonight will undoubtedly inspire conversation around the world. Neil was a professor of physics at Princeton University, and then the chair of mathematical physics at the University of Cambridge, before taking his post here at Perimeter. As well as developing fundamental theories of the cosmos, he has led efforts to determine their predictions and to test those predictions through observation. With Stephen Hawking, he developed the Hawking-Turok instanton theory, which describes the birth of inflationary universes. With Paul Steinhardt, he developed a cyclic universe scenario. Born in South Africa, Neil founded the African Institute for Mathematical Sciences, a pan-African network of educational centers for education and research. The work has been recognized by awards from the World Summit on Innovation and Entrepreneurship, the World Innovation Summit on Education, and a TED Prize. This past June, Neil hosted a special conference here at Perimeter called Convergence. Convergence brought together the leading minds in physics to probe some of the most promising questions and chart a path for 21st century physics. Tonight, that discussion is continued, and it provides an opportunity for Neil to share with us why he is so excited about the future of physics. Please join me in welcoming to the stage with his talk, The Astonishing Simplicity of Everything, the director of Perimeter Institute, Dr. Neil Turok.
Thank you. Thank you. Thank you. Thank you, everybody. Thank you so much for coming. Thank you for your enthusiasm, which really buoys us and drives this place forward. You are the people who recruited me to Waterloo. When I came and gave a public lecture here, I realized something special in the community here, and you continue to enthuse all of our visiting speakers. And it's very humbling for me to speak this year because there are 2 Nobel Prize winners coming, at least, this year, and many other fantastic talks. So thanks very much. Now, of course, the biggest pleasure in being director of Perimeter is the people I meet and the people I get to invite to join in our mission. And one of those very special people is a physicist. We're always a bit careful about having physicists on our governing board because we have our own approach, and we want to set our own path. So when we invite physicists to join us, we have to be sure they're really going to be in tune with us, and above all, wise people. And the person I'm talking about, of course, is today's Nobel Prize winner, Art McDonald. So should say yesterday, I should say. Art, we had no hesitation about inviting him in 2011 to join the board of Perimeter. He is one of those unique figures in physics with his wisdom, intelligence, experience, and incredible ambition to go after the hardest problems in physics. He's what I call a real person, and I'm what I call an imaginary person. And I'll explain that more in the talk. But art really builds things. And in many ways, he pioneered what we're trying to do at Perimeter. He built the world's top laboratory for studying neutrinos in Sudbury. And they discovered how neutrinos work, how they travel from the sun to us, how they change flavors on the way. And this is really an incredible pointer to new physics beyond the standard model. So, but let me not say any more. Let's have the video of Art.
I have been the director of the Sudbury Neutrino Observatory, which is the first major experiment in what has now become SNO Lab, the international underground facility near Sudbury, Ontario. The Sudbury Neutrino Observatory, or SNO, used 1,000 tons of heavy water to make measurements of neutrinos from the sun, benefiting from being 2 kilometers underground to shield out cosmic radiation and therefore get a very low background detector. We were able to observe these neutrinos at roughly 1 an hour, and in the process of these measurements could resolve the question of whether neutrinos from the sun changed their type in transit to the Earth. We could be definitive about that because with the heavy water we could measure the type produced in the core of the sun and also the sum of all types of neutrinos. And comparing those two, we found that only about 1/3 of the neutrinos reaching us were actually the electron neutrinos produced in the core. This meant that, first of all, we had a clear indication that neutrinos change their flavor and therefore have a finite mass. And we were also able to determine that the models of how the sun burns, and in particular the nuclear reaction that we were measuring, was being calculated very accurately. So those measurements were quite significant, it was felt, in the world of physics and astrophysics.
So I have to thank Art for his impeccable timing in doing all his work to ensure that he won the Nobel Prize just before my public lecture. So we promised Nobel Prizes, and there's the first. The title of my talk is The Astonishing Simplicity of Everything. And I have to begin by saying that I told this title to a friend of mine a week ago who has teenage kids, and he said, "Oh yeah, the world seems pretty complicated to me." And so I'm going to be very careful by defining what I mean by simplicity. I hope to share with you some of the most amazing discoveries we have made recently about the universe, and the fact they're pointing us in new directions for our understanding of the universe, which is extremely exciting. So what do I mean by simplicity? Well, for a physicist, simplicity means simple concepts, or concepts which unify. They bring together disparate ideas and disparate knowledge, make sense of them, and simplify. I often like to say that a theoretical physicist is somebody who has a terrible memory, and therefore they want to make sure they're on top of everything while they remember nothing. And or as little as possible. So simple concepts are ones which allow us to explain the most we possibly can from the least possible level. So I'm going to tell you about the recent discoveries and why they show us that they are pointing us to ways in which the universe has regular, predictable behavior, which we do not yet understand. And so this is pointing us at new, simple principles, which we're trying to discover. So here's a rather beautiful picture of the whole universe that we can see. And we're in the middle, in the solar system, going around the sun. But there's this vast expanse of space full of galaxies. And of course, as we look outwards in space, we're seeing backwards in time, just because light takes time to reach us. So as we get to the outer reaches of the region we see this cosmic web, the structure of the universe as it began to form at early times. And we go further back, there's a dark stripe, which is the Dark Ages, we call it. And just before the Dark Ages is a bright red ring. That red ring is the hot plasma of the very early universe, the earliest thing we can see. And if we could probe through it, as we will be able to do one day with gravitational waves, we will be able to see right back to the singularity itself, the moment when space and matter emerged, and when everything was formed. Now, our place in this universe is in the middle, obviously. That's not because we're in a special place. Every other place in the universe, as far as we know, would have a similar picture around it, would be surrounded by a similar picture. But we're also in the middle in terms of scale. You see, there's a definite size of this volume of space. There's a number of galaxies, about 100 billion galaxies we can see, each one containing 100 billion stars. But what we've discovered recently is that space, empty space, is full of dark energy. It's a form of energy which is accelerating the expansion of the universe. The universe is growing in size, and the expansion is carrying other things away from us. And due to the dark energy, it's expanding faster and faster. And so it's taking the stuff, even the most distant galaxies we can see, taking them away from us more and more rapidly. As it does so, we'll see them turn red, go dimmer and dimmer, and disappear. And we will never see anything beyond those galaxies because of the dark energy. So there is a scale, there's a fundamental scale in physics. It's the scale defined by the dark energy, which limits the region of the universe we will ever see. And so that's the largest scale we know of. It's about 10 to the power 25 meters. The tiniest scale we know of in the universe is what we call the Planck scale. And that you can see right at the edge of the picture. You see, if we look out as far as we can, go backwards in time, following the universe back to the singularity. Imagine we are following a light wave that's traveling through this plasma. The whole universe is shrinking, the light wave is shrinking, it'll become more and more energetic. The Planck time is the moment those light waves are so energetic that two light waves encountering each other would form a black hole. And so they would disappear. We can't describe them after that, they'd be inside a black hole. That's called the Planck scale, a scale so tiny that if you try to squeeze a light wave into it, it has enough energy to collapse the space around it and make a black hole. So that's called the Planck length, and that's about 10 to the minus 35 meters. So we can go from 10 to the plus 25 to 10 to the minus 35. Now where are we? Well, the size of a living cell is about 10 to the minus 5, which is halfway between the two. In mathematical terms, we say it's the geometric mean. We live in the middle between the largest scale in physics, which defines the region we will ultimately see, and the tiniest scale, which is so tiny we can't even talk about space and time on smaller scales than that. So we're in the messy middle. And the astonishing thing about recent discoveries in physics is they tell us the universe is surprisingly simple and regular on the tiniest scale and on the hugest scale. It's only complicated in the middle. And so that's the sort of summary of my talk. I can take questions now. As I mentioned, we can look at it in space, we can look at it in time. If you look at any region of the universe, it would have a history like this, as far as we know. So you trace it backwards in time, it shrinks down to zero size. The space literally shrinks away to nothing. As you follow it forward in time, it's dominated by this dark energy, which is causing it to expand more and more rapidly. We don't know where it all came from. We don't know where it's all going. These are very profound clues, which we finally have the means to get to grips with. So here's a real picture. This is a picture made by the Planck satellite, the European Space Agency Planck satellite. It shows a projection of the whole sky which surrounds us, the spherical sky. So it's like a map from an atlas. And the pattern it shows is the pattern of the variations in the density across the sky. Those variations in density create a variation in temperature, and where the sky is hotter, you see a brighter radiation coming from it. Where it's colder, you see a less bright radiation. And that's what this picture is showing. Now, you can see immediately this picture has amazing symmetry. The universe is not a random mess on large scales. Why? Because these variations in the temperature are only 1 part in 100,000 from place to place. So to first approximation, the universe is absolutely uniform in all directions. Very strange, because given that we're only receiving the light from now from these places on opposite sides of us, how did they know to be at the same temperature? They can't have communicated with each other through light because we're only receiving light from them now. But nevertheless, they are very close to the same temperature, these points which surround us in all directions on the sky. The second thing, which is not obvious in this picture, is what I call synchronicity. See, if you take a bell which vibrates at various tones and you strike it, all those vibrations are synchronized because they all got excited at the same time. And so if you look at the pattern in the sound of a bell, you would be able to detect that it was struck at one moment. And that's what happens with these variations of temperature. They were excited at the Big Bang. And subsequent to that, they have oscillated a certain number of times. And so you can't see it in the map. So what you do is a mathematical trick called Fourier analysis, which I'll talk about a little later. So you essentially look at this picture, but in a slightly different way. And what you see is this, that when you analyze the amplitude or strength of variations in temperature on different scales on the sky. See, in a different scale, it's like the length of a string of a musical instrument. It will vibrate with a different pitch. And so I call this pitch, the amplitude against pitch of the sky. And what you find are these wonderful peaks. These are waves which have oscillated once. They've hit their maximum just when we see them. These ones have hit their first zero. These have hit their second maximum. So we literally see the universe is a giant bell, was struck at the Big Bang, and everything is synchronized. So there's remarkable symmetry in this pattern. The universe is not a complicated thing at all. In fact, the whole universe is as simple as the simplest atom. If you think about a hydrogen atom, you know, how many numbers do you need to describe an atom? An atom's a pretty simple thing. You've got a nucleus, you've got an electron going around it, you've got the force of electrical attraction between the nucleus and the atom. And you've got a few details of quantum theory too, which I'll come to. But an atom is a pretty simple thing. Well, it turns out the universe, to describe the structure, you need one number, which is this number, 1 part in 100,000. That number describes the structure of the universe. Fewer numbers than you need to describe a single atom. So the universe turns out to be the simplest thing we know. The whole thing is the simplest thing we know. Isn't that amazing? And this is how to go from that pattern, which looks random, looks like a messy pattern. You know, it looks pretty random and unimpressive. But if I show you this pattern, so the way I've built up this pattern is by adding together waves of different wavelengths. And I've added them all up so they, oops, let me do it again. When I add together the waves of different wavelengths, the result, it's giving me trouble, but the result looks pretty random. When you go to this Fourier picture of seeing how strong was each wave, they're all the same. And so the universe we see doesn't distinguish between scales, doesn't distinguish between how big something is. A wave that stretches right across the universe has the same strength as one 100 times or 1,000,000 times smaller. They're all the same. It's an unbelievably simple pattern that came out of the Big Bang. And here it is, more graphically. Here, imagine a sphere carved through space on which we can see what the hot plasma of the universe is doing as it expands. And you can see it's oscillating with these waves. And as the universe expands, the scale gets bigger and bigger and bigger. And ultimately, this will be the sphere that surrounds us today. And when we look out, we're in the inside of the sphere, looking out, and we will see this pattern, which is scale-free. Now I want to show you, this is a little bit of recent research with my collaborator at the University of Toronto. This is us trying to calculate what happened in the first billionth of a second after the Big Bang. So the beginning of the movie, it loops around, but the beginning of the movie are these smooth waves filling space. This is the end. Let's wait for the beginning again. There, you see these smooth waves filling space. They look very benign. But as they evolve, you see they form shocks, sharp edges. And these shocks then collide, and they will generate all kinds of interesting effects. So this wasn't understood until very recently, and it's an example of how we are following our knowledge back further and further into the deep past of the Big Bang. This is probing energies beyond what the Large Hadron Collider can do, but of course only theoretically. Okay, so that's the big picture. The universe has turned out to be stunningly simple. Most theorists I know are dismayed by this, because it means that most of the models have turned out wrong. Because the models were all predicting, oh, you should get this or that, or this specific feature or that specific feature. And what's happened is the universe has surprised everyone, that it's simpler than any of our models can explain. The same thing happened at the Large Hadron Collider, and I'm not going to dwell on it, but they were looking for the Higgs boson, they found the Higgs boson. Most of the theorists in the world were predicting lots of other particles would come along with the Higgs boson. But the Higgs is pretty lonely. And again, nature has used the simplest possible way. It's so simple we don't understand how nature got away with it. So the coming year is very exciting at the Large Hadron Collider. if they don't see supersymmetry, which was one of the favorite theoretical paradigms. If they don't see it, it will be a disaster for many people who've spent decades working on that idea. But personally, I would welcome it. I mean, as a theorist, you should be happy when you're wrong, because at least it meant your idea was testable, was worth talking about. Okay? It was worth talking about. I mean, if you can't be proven wrong, it's not worth talking about. So, but I'm not sure other people share that view. So let's go back to the beginning of physics and mathematics. Because the simplicity I've just told you about, we don't yet understand. Okay? Are we ever going to understand it? I want to persuade you the answer is certainly yes. In order to make the case, I have to show you how far we've come already. And it's ridiculous how far we've come, of course, when you think how briefly we've been thinking about these problems. So let's go back to the beginning of mathematics in Africa. 22,000 years ago, somebody in the Congo carved these markings on a bone, the Ishango bone. There are 60 notches on either side of the bone in very particular arithmetical patterns. And people who've analyzed the bone have concluded that this is not a coincidence. They weren't just playing with notches, they were studying patterns in numbers. So that's the beginning of mathematics, and you think of the significance of that. I mean, where would we be without mathematics? The idea of number is a strange thing. I mean, 1 or 2 or 3 don't exist as entities in the world. These are abstractions, idealizations, yet they work. You couldn't do finance without numbers. Actually, some people do finance without numbers, and it doesn't work. But you shouldn't do finance without numbers. So numbers are incredibly powerful. And again, this is a feature of simple ideas. They are unifying, they are unbelievably powerful, and they open the door to the future. And that's what happened in Africa. This you will probably all remember from high school, Pythagoras' theorem. This was the transition of mathematics into a theorem-proving subject, where you tried to prove things. You know, so what is mathematics, after all? Mathematics is just logic. It's the crystallization of logic. The ideas which are considered proven in mathematics are the most proven things we know, more or less by definition. Okay? That's what you mean by mathematical proof. So physics is a little different. Okay? Physics is logic applied to the real world. So fortunately, the real world does seem to obey logical rules, mathematical rules. And it's a physicist's task to discover what those rules are in nature. Mathematicians don't mind if the rules are relevant or not to nature, as long as they are logically consistent. So Pythagoras, actually, didn't discover this. This result was known, but Pythagoras thought about how to prove it. That was the novelty. So we have a triangle with 3 sides, A, B, and C. And as you know, Pythagoras' theorem is that the area of the squares on the 2 shorter sides will sum to be the same as the area on the long side. And that was the first theorem in mathematics. Now here's a rather beautiful proof of this theorem, which will use some ideas which I'll need later. By the way, let me just comment on the notion of proof. A friend of mine in Africa once told me that the significance of proof, mathematical proof, it's an African mathematician, mathematical proof is connected to justice. Because in ancient Greece, one of their innovations was that you couldn't just accuse someone of something, without showing, without arguing, without conclusively producing evidence that they'd done something wrong. So the idea of proof came along at the same time as mathematical proof. So logic and justice are actually very closely interconnected. So let's go back to our triangle, and you'll notice one of the angles is a right angle. That's the theorem only applies to right angle triangles. The other two angles I've labeled, and now we've drawn a perpendicular from this corner to the hypotenuse, the long line. And what's special about these two angles is that they are shared between two triangles. You see, this angle is obviously one of the three angles of the big triangle, but it's also one of the angles of this little triangle. This angle is shared between the medium triangle and the big triangle. Now, you know, if two angles are the same in two triangles, the third angle is fixed. Okay, so it means that all three angles in all three triangles have to be the same. Therefore, the triangles must be the same shape. If they're the same shape, it just means they're scaled up versions of each other. Okay? Now, what is the area of a triangle? The area of a triangle, well, you know it's half base times height, but even more primitively, you'd say it's a square. An area is a square of a length. Take a triangle of some shape, and I scale it up, the area is going to scale up like the square. Okay? So the area of this triangle is b squared times some number. The area of this one is c squared times the same number, and a squared times the same number. Why is it b, c, and a? This is the hypotenuse of the big triangle, that's the hypotenuse of the little triangle, and so on. So you see immediately that because the areas of the two smaller triangles are the same as the bigger triangle, you must have this formula. The square of a plus the square of b is the square of c. Okay, so that's a rather nice argument that for any right-angled triangle, this equation must be true. Now I want to introduce a more bizarre mathematical character, and it took people 2,000 years to make the next great leap in mathematics. Okay, geometry was pretty important. With Pythagoras' theorem, you could build pyramids and structures, and architects wouldn't make a living without Pythagoras' theorem. But it took 2,000 years before the next huge leap forward in mathematics, and that came about with this strange character I. So the problem was that the problem arose in solving equations. Mathematicians like to solve equations, that's what they do. So you write down x squared plus 3x plus 2 equals 0, or x to the 5th plus x to the 4th. So they were busy in the 16th century solving these equations. In fact, they had competitions to solve equations. And so nobles would set equations, and then people would arrive, and they would work desperately for a couple of days, and the one who solved the equation would win the prize. So there was a guy who, at the time, who discovered that if he imagined a number whose square was -1, then he could actually solve lots of equations. And he kept the trick secret. It wasn't published for 20 or 30 years, and then finally word got out, and this number I, the imaginary number, came into being. So it's a very strange thing. It sounds very counterintuitive. How can I have a number whose square is negative? We all learned in high school that a number times itself. Two negative numbers, a negative number times itself will give a positive number. So it's obviously not a negative number. It's not a real number at all. It's an imaginary number. Actually, in my inaugural lecture in Cambridge, I introduced this number and I didn't really explain it. And my brother is an economist who happened to be at the lecture, and I talked about imaginary things. And he said to me at the end of the lecture, if you allow yourself imaginary things, I'm not surprised you can do anything. But this imaginary number is very, very, very precise. There's no ambiguity about it. It's not a fiction as far as mathematicians are concerned. It's the real deal, this I. Now why? Because as soon as you've introduced it, you can solve all equations. Okay, so it's rather easy to show. I won't show it in detail, but it's rather easy to show using the concepts I will describe that any possible equation has a solution. Furthermore, any equation which, say I wrote down x to the 23 plus some number times x to the 22 and so on equals 0, there will be 23 solutions of that equation. And that's rather easy to see. If somebody wants to ask a question afterwards, be happy to answer it. It's called a fundamental theorem of algebra. So all of a sudden, with this one extra character in the game, a problem that had seemed impossibly complicated and difficult, because some equations seemed to have solutions, some didn't have solutions. Now all equations were on the same footing, and they all had solutions. It's an incredibly powerful, simple idea. Once people had, now it relates to Pythagoras' theorem as follows. Once you have the idea that you have this guy I, and this is a very valuable idea. It's not an iPhone or an iPad. It really annoys me when that was branded as I, because this is the I. Okay, I'm sorry. This I will be here for eternity. I'm not sure about the other one. Okay, so we take the I. Now, we are going to enlarge our space of numbers. We have a number x, which could be any number, from -infinity to infinity, an ordinary number. And then we have another kind of number, which is a multiple of I. So, and we put the two things together. We say, I'm going to allow numbers which have a real part, the x part, and the imaginary part, which is the multiple of I. Okay, so the dimension, suddenly I've gone to numbers not being on a line. They're now in two dimensions. I can go along the line. I can also go in the I direction. And so I can go along x and up in y, and I get this number, x plus iy. Now, one of the most basic and important functions in mathematics is the exponential function. We all know about exponentials because of inflation in prices. That's a bad thing. If prices rise by 10% per year, the prices are going to go through the roof. And they will follow exactly this law. If the x is 0.1 to represent the 10% growth per year, it will grow as e to the 0.1, where e is the number invented by Euler. Euler, most brilliant mathematician in the world in the 18th century. So we know about exponential growth. It applies to a huge number of things. So if you have bacteria multiplying, each bacterium doubles every 20 minutes, then the population of bacteria will grow exponentially. Compound interest, many, many things follow this law. In terms of mathematics, this is the simplest solution to one of the simplest equations, which is that the derivative of a function, meaning the slope, is equal to the function. So it's telling you that how much the function will change as you increase, go along in x. The change in the function is proportional to the function. Solution of that equation is this exponential function. Okay, so it's a very basic function in mathematics. Now, it's not very good for modeling the real world. Sometimes it's good, because sometimes really things do go crazy, okay? But a lot of what happens in the world is rather regular. I mean, things don't just keep growing forever. So Euler, who invented this kind of mathematics, differential equations and these functions, decided, what happens if I exponentiate? You see, this is exponentiating a real number. So he said, what happens if I exponentiate this imaginary number? Okay, a very natural question. Does it also go through the roof? Well, no. When you exponentiate the imaginary number, it goes round in a circle. Okay? So the exponential of an imaginary number times theta, where theta is a real number, it's an angle, actually. It's an angle here. It gives you the trigonometric functions, cosines and sines. And if you remember your geometry, the cosine is this side divided by that, and the sine is this side divided by that. And I've taken out the scale. I've just set the hypotenuse to be 1. So you see the fact that the exponential of an imaginary number gives you a point on a circle. And so as theta runs, this angle theta can grow, the point is just going to go running around a circle. Now that's like a lot of natural phenomena. So if something in nature goes back and forth, it's going to be described by mathematics like this. Whereas if it goes one way and explodes, it will be real numbers. Okay? So that's what Euler discovered. This formula here connects differential equations, which give you exponentials, to algebra, which gives you I, to geometry, which gives you these. Okay? It's been called the most amazing formula in mathematics. So I hope you're beginning to be a little bit impressed with I. Okay? There's a lot of good stuff for you at very little